Hi everybody, this is the lecture on the final section of the course, section 7.4. So section 7.4 is mostly about integration with polar curves. However, there's a little bit about derivatives and tangent lines, so let's cover that. Given a polar curve r equals f of theta, so this is the way we've been looking at defining curves in the xy plane with polar coordinates, is looking at functions r equals f of theta, mostly, although there are other types of things you might look at. Using the relation, right, that x is r cosine theta and y is r sine theta in general for polar coordinates. Since r is f of theta right here, you can replace in this expression the r's with f of theta. So now x is just defined in terms of theta, and y is just defined in terms of theta. Right? So what that gives you is that a polar curve r equals f of theta is equivalent to a specific example of a parametrically defined curve, right? Instead of t, we have theta, right? A parametrically defined curve is when x was equal to h of t and y is equal to j of t. Oops. Right? X was a function of t and y was a function of t. So instead of t here, we have a function of theta. Right? So it's just a special case of that where it's f of theta cosine and f of theta sine theta. So now the derivative dy dx, which gives you the slopes of those tangent lines, is determined using the same technique that we did in section 7.2. dy dx is dy d theta over dx d theta, right? The d thetas cancel, right, which gives you the dy dx. And you get f of theta cosine theta, so you use the product rule. Right? So the derivative of the top derivative of sine is cosine times f, plus the derivative of f times sine. Right? So that's just using the product rule, f of theta cosine theta plus f prime of theta sine theta, divided by the derivative of cosine is minus sine. So minus sine times f of theta plus f prime of theta times cosine theta. So just using the product rule. So let's use this derivative to help graph the polar curve r equals 1 plus cosine of theta. Okay, well, the way we were looking at these in the previous section, right, the cosine theta, moves in steps. Starts from 1, then it goes to 0, then it goes to -1, then it comes back up to 0, and then it goes to 1 again. Right, and it does this in chunks of 90 degrees. That's pi over 2, that's pi, 3 pi over 2, and that's 2 pi. Right, so let's look at theta in chunks of 90 degrees. So 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. So at 0, 1 plus cosine theta is 2. And then at 90, 1 plus cosine theta is just 1. So we go from 2 down to 1, and then from 1 down to 0, and from 0 back to 1, and then from 1 to 2. So here's a rough sketch. Right? 0 degrees, radius 2, down to radius 1 at 90 degrees, down to radius 0 at 180 degrees, up to radius 1 at 270, up to radius 2 at 360. All right, but what are the slopes at various points along this curve? And notice you've got horizontal and vertical slopes going on too. And what's going on at this point? I mean, there's something kind of strange going on there. What's happening there? Well, let's look at the derivative. So dy dx is, so x is r cosine, y is r sine theta. So dy dx is using the product rule. Right, the derivative of cosine is minus sine times sine, plus derivative of sine is cosine times 1 plus cosine, divided by this. So it could also be thought of as this right here. So at 90 degrees and at 270 degrees, we get slopes of 1 and negative 1. So it's 45 degrees and 45 degrees positive and 45 degrees negative. And then at pi theta equal to pi, dy dx doesn't exist. Right, because you're dividing by 0. Right, so essentially what's got to be going on here is that you got to have some non-differentiable point. And when were curves not differentiable? When they are not continuous, this is continuous, that's fine. It's just that it's not smooth. So it has to be some non-smooth point there. And where are the horizontal and the vertical slopes? Horizontal slopes right, so that happens when the numerator is 0. So that's when cosine 2 theta is cosine theta. Right, that's when the numerator of that derivative is equal to 0. So let's see if we can't fix this up a little bit. So cosine 2 theta is cosine squared theta minus sine squared theta plus cosine theta. So this is 1 minus cosine squared, so that's 2 cosine squared theta minus or plus cosine theta minus 1. Right, so factoring that, this is 2 cosine theta, 1 cosine of theta, 1. So this is plus 1 minus 1. Right, so either cosine of theta is a half, right, which is at theta equal to 60 and minus 60 degrees, or theta is equal to negative 1, which is at pi, and that's where that non-differentiable point is coming from. So it's 60 and minus 60 degrees. And then vertical slopes, that's where the denominator of that function is going to be equal to 0, and you don't otherwise have a non-differentiable point. So that's where sine 2 theta plus sine theta is 0. So that's 2 sine theta cosine theta plus sine theta equal to 0. So factoring out sine theta, 2 cosine theta plus 1 is 0. So that's where sine of theta is 0. So that's at theta equal to 0 and pi. And where cosine of theta is negative 1/2. And that's at theta equal to 2 pi over 3 and minus 2 pi over 3. So now we've got like a much nicer way, a definite guide to drawing this curve. So 1, 2, and then at 60 degrees, we're at 3/2. So 60 degrees, we're at 3/2. 120 degrees, and then minus 60 and minus 120. So this is where we're going to get the horizontal slopes. This is where we get the vertical slope, and then here the slope is 1. So that's a slope of +1. This is a slope of -1, or this is a slope of +1. This is a slope of -1. So 45 degrees in each of these spots. 45 degrees this way. Alright, so horizontal slope, 45 degrees, vertical slope, and then a sharp non-differentiable point. So then a vertical slope, 45 degree slope, 0 slope, and there it is. So horizontal slopes here, I didn't quite get it right. Here and here. I didn't quite get it right. Tell you what, let's just shift this instead to where that vertical slope, the horizontal slope is. So that's a horizontal slope. Horizontal slope. And these right here are the vertical slopes. And that's a slope of 45 degrees right there. Make those red. So 45, 0, 0, 45, vertical, vertical. That curve could be a little better right there. Vertical slopes. It's supposed to be black. Vertical slope. All right. So that's a much sort of more in-depth and detailed picture now that we know these slope values. Okay. So you can apply that to getting, more detailed drawings for other curves as well, for those 3-leaf roses, 4-leaf roses, spirals, and all kinds of other things. Okay. So, let me mark off those angles. Pi over 3, 2 pi over 3, 3, 4 pi over 3, 5 pi over 3. Alright, how about some areas? So suppose we have r equals f of theta, and we're going from an angle alpha to beta. So this is the curve r equals f of theta. This is the line r equals alpha, or theta equals alpha. And this is the line theta equals beta. So angle alpha, angle beta, and then this is the curve r equals f of theta, and what is going to be this area inside here. Okay? Alright, so take the interval theta equals alpha to theta equals beta, and we cut it up into subintervals. Alright, so this is theta equal to alpha, theta equal to beta. Delta theta is beta minus alpha over n, and then theta I is equal to alpha plus I delta theta. So you've got various subdivisions here of the interval. So theta 1, theta 2, theta 3. Theta 0 and theta n. So now you've got this curve r equals f of theta, and what you do is you take the radius of the left-hand side of each sector. So we've got these sectors, right? And what we're going to do is we're going to take this point and now make a circular sector of that radius. So we estimate using circular sectors. Oops. Let me do a different looking curve to perhaps make that a little bit clearer. Let's just go like this. Alright, so here. So now you make a circular sector of that radius. A circular sector of this radius. Circular sector, circular sectors. So now we're interested in calculating the area of each circular sector. So we estimate the area with circular sectors having angle delta theta. Okay, well, what's that area? Well, we know what the area of the whole circle is. It's pi times the radius squared. Okay? So here you've got this angle delta theta, and then you've got some radius, which is f of theta I. But let's just call this angle, let's see, instead of theta, we'll call it angle alpha, beta, gamma. Angle gamma. And this length right here, we'll just call it L, gamma and L, delta. Angle delta, length L. Okay, so the area of the whole circle is pi times L squared, which is equal to 2 pi over 2 L squared, right? Where 2 pi is a full rotation. Of the circle. So the area of the sector is equal to, well, it's 1/2 the angle, right? Times the radius squared. It's 1/2 L squared times the angle delta, where delta is in radians. Right? So instead of 1/2 L squared 2 pi, 1/2 L squared 2 pi, where 2 pi is a full rotation of the circle, it's just 1/2 L squared delta, where delta is some, fraction of the circle. So the area enclosed by r equals f of theta is approximately the sum, I equals 1 to n, of the areas of the sectors, which is equal to the sum, I equals 1 to n. 1/2, well, what's the radius? Well, just put the radius squared times delta theta, which is equal to the sum I equals 1 to n, 1 half, this is f of theta, squared times delta theta. Right, so this is the function f of theta times delta theta. So, and you know, that's the approximation, and the approximation gets better as n towards infinity. N goes towards infinity. So the area is equal to the limit as n goes to infinity. The sum I equals 1 to n, 1 half f of theta I delta theta. So that's the integral from alpha to beta. 1 half f of theta squared d theta. And that's it. Right, so that's the area enclosed by a polar curve between two angles. So, for example, what is the area enclosed by the cardioid r equals 1 plus cosine theta, that one that we just graphed up top. All right, this one here. Well, this area is the integral from 0 to 2 pi, because we're going from 2 down to 1, down to 0, back to 1, up to 2. All right, so that's a full rotation of 180 degrees, and you get this heart shape here. So it's the area from 0 to 2 pi, 1 half r squared d theta, which is equal to integral from 0 to 2 pi, 1 half 1 plus cosine theta squared d theta. So this is the area, the integral from 0 to 2 pi, 1 half 1 plus 2 cosine theta m plus cosine squared theta d theta. So it's equal to integral from 0 to 2 pi, 1 half d theta, plus integral from 0 to 2 pi cosine theta. That one's 0. Right, because you're just taking one iteration of the sine curve, or cosine curve. Right, and that area is going to be 0 because it's, you know, these two areas are equal to those two areas. So that one's 0. Plus the integral from 0 to 2 pi, 1 half cosine squared theta d theta. So this area is, this integral is pi, because it's just a constant, so it's a half times 2 pi, it's just pi. And this is the 1/4, using now the double angle formula, 1 plus cosine 2 theta d theta. So it's pi plus 1/4, the integral from 0 to 2 pi d theta, plus 1/4, the integral from 0 to 2 pi cosine 2 theta. So this is two iterations of the cosine curve, so that one is 0. And this one is 2 pi times 1/4, pi over 2. So this is 3 pi over 2. So that's the total area enclosed by that cardioid. Okay? All right. So final example of an integral using polar coordinates would be using an integral to calculate arc length. Right, so parametrically, defined curve y equals f of t, or x equals f of t, y equals g of t, a less than or equal to t less than or equal to b, has arc length integral from a to b square root dx dt squared plus dy dt squared dt. And this is from section 7.2. All right. So here with a polar curve, given y or r equals f of theta, we again get that x is f of theta cosine theta, y is f of theta sine theta. So arc length for alpha less than or equal to theta less than or equal to beta for the curve is integral from alpha to beta square root dx d theta squared plus dy d theta squared d theta. So this is equal to the integral from alpha to beta. So dx d theta is f prime of theta cosine theta minus f of theta sine theta squared plus dy d theta is f of theta cosine, or let's put the prime first, f prime of theta sine theta plus f of theta cosine theta squared. So this is equal to the integral from alpha to beta. Okay. So f prime of theta squared cosine squared theta plus f of theta sine theta, f of theta squared sine theta squared plus 2f of theta f prime of theta sine theta cosine theta plus square this one, f prime of theta squared sine squared theta plus f of theta squared cosine squared theta. Oh, this one was a minus 2. And then this one is plus 2 f theta f prime theta sine theta cosine theta. So that square root is distributed all the way through there. I shall leave that out. And that whole thing d theta. So this and this cancel. These add to 1 with a common factor in the front. So that's just f prime of theta squared plus f of theta squared. Because here again you got f of theta squared sine squared plus f of theta squared cosine squared. So that's just f of theta squared. So there's the arc length formula for curves in polar coordinates. Okay? So, for example, good example. Let's do r equals e to the theta. So this is an exponential spiral. So that's a spiral that's really spiraling out of control really fast. So let's do, we'll say 2 pi. Right, right? So we go around once, twice. So 0 less than or equal to theta less than or equal to 2 pi. So r of theta is e to the theta, and dr d theta is still just e to the theta. Right, so that's another, we can do it in terms of r as well. Integral from alpha to beta, dr d theta squared plus just r squared d theta. So you could write it both ways. So dr d theta and just r. So here r and dr d theta are the same. So the length is the integral from 0 to 2 pi e to the 2 theta plus e to the 2 theta d theta. So this is the integral from 0 to 2 pi 2 e to the 2 theta d theta. So that's square root 2 e integral from 0 to 2 pi e to the theta. Antiderivative is e to the theta from 0 to 2 pi. Oh, 2 pi. Yeah, I was going to do 4 pi. Well, let's just do 2 pi. It's fine. That's not even 2 pi what I'm showing there. That's like 2 pi plus 90. So there it is, 0 to 2 pi. So this is root 2 e to the 2 pi minus e to the 0, which is 1. All right, so that's the arc length of that exponential spiral. Okay, so a lot more examples in the homework, and we will go over those during discussions, but that is the lecture for this section.